Hi, and welcome to more statistics charts using the data that we gathered from our convenience sample of potatoes, that bag of potatoes that we measured the lengths and the widths. So as you'll recall, we measured the length and width of the potato and in each of the potatoes in the bag, and then we went ahead and decided to do some univariate analysis, or the analysis of just one of the values and how it varies. And so we decided to choose the length parameter for the potatoes, how long they are. So you can see here in the picture on the left, the table, our workspace here, where we sorted the potatoes by length. The shortest potato is on the bottom and the longest potato is on the top. And we represented some information about the lengths of those potatoes using a whisker, box and whisker plot. So the box plot, or the box and whisker plot, shows us information about quartiles. Well, quartile is just a fancy name for 1/4 of your sample set. So our sample set had 24 potatoes. So half of them is 12 potatoes, and half of that again is 6 potatoes. So 6 potatoes is essentially the quartile. And we can use the box and whisker plot to see the lengths of the potatoes in each of the quartiles. The 6 smallest potatoes on the bottom have a range of length values as shown in the box and whisker plot, and the length of, let's say, the 6 longest potatoes have that top range of lengths in the box and whisker plot. So the box and whisker plot, by seeing the ends of the whiskers and the top and bottom of the box, they basically show the length ranges for each of those 1/4 of our sample set, or quartile ranges is the proper statistics naming for it. So the quartile ranges are shown in the box and whisker plot. Also the median, which is essentially the halfway line. In other words, the length that would split our sample set in half, where half of the potatoes are shorter than the median length and half of the potatoes are longer than the median length. I guess if we had an odd number of potatoes, the median length would be the length of that middle potato. But either way, it's basically the number, the length in inches that would split our sample set in half. We also have the mean, which is the average or the expected length of a potato. And we learned last time that just because we call it the expected length of a potato, we certainly don't expect to randomly pick a potato and have it be exactly that length. It's over many measurements. If we were to measure many potatoes and then take their average, that's what the mean stands for. That's the average. And finally, just as you had the ranges of the quartiles, you also have the total range shown in your box and whisker plot. So that's really what we covered last time. That's as far as we got in terms of visualizing the data. But instead of visualizing by how many potatoes have a certain range length, instead well, let me put it a different way. What this plot has done is it's done a quartile. It's divided our sample set into 4 equal-sized sample sets, each having 6 potatoes. And then it shows you the length range of each of those 4 sets, right? So you can see here from the box and whisker plot, the longest 6 potatoes have a wider range of lengths than the smallest 6 potatoes that are much narrower. And that's really trying to say that just there are more potatoes in a narrower range of values. But what if instead of looking at our data in terms of how many potatoes and then the range of values, instead we chopped up our data into ranges of values that were equal sizes. So the box and whisker plot has chopped up the data by chopping up our sample into equal sizes, 6 potatoes each. But what if we instead chopped up our length ranges into equal sizes? Let's say a certain number of inches. How many potatoes fall into this range of length, and how many potatoes fall into that range of length? It's a different way of looking at the same data, and it can reveal different information. So let's go ahead and take a look at that. So instead of dividing the sample into quartiles, or basically equal numbers of potatoes, what we're going to do is we're going to divide the sample into a histogram, and that is basically equal ranges of lengths. So in this picture, I kind of flipped it upside down. The smallest potatoes on the top and the biggest potatoes on the bottom. But you can see I've put some blue painter's tape showing equally spaced ranges of lengths. So when I do this, it's important to make sure that each of those ranges of lengths is equal for each group. So what we've done is we've chosen ranges that are 0.3 inches wide, so that the very top group of potatoes with the smallest lengths are anywhere from 3.2 inches up to 3.5 inches. So the width of that range is 0.3 inches. Same thing, the next one down is 3.5 up to 3.8 inches, but look how many more potatoes fall into that range. So you can see the labels of the ranges, they're all labeled here, all the way up to 4.7 up to 5 inch in length of potatoes. So the ranges of lengths are all 0.3 inches wide. So they're equal ranges, but they contain, each has a different number of potatoes that fall into those ranges. We call this a histogram. Usually the histogram is drawn with like a bar chart. So here I've just simply counted the number of potatoes from our sample that fall into those equally spaced length ranges. So the very smallest range, 3.2 to 3.5 inches, there were only 2 potatoes that fell into there. So I'll draw a little stick or a line that has 2 of those blocks representing 2 potatoes. And then the next range, 3.5 up to 3.8 inches, that had many more potatoes. I think if I'm counting quickly, it looked like 9 potatoes. So I've drawn a longer stack of boxes, if you will. So the histogram is basically kind of like a bar chart, you know, where the length of the bars indicates how many potatoes or how many samples from our sample set fall into those equally spaced length ranges that we decided on earlier. So now I've turned it sideways, and you can see clearly by the height of those different bars that we can see how many potatoes from our sample set fell into those equally spaced ranges. So this is basically what we call a completed histogram chart for the lengths of the sample set of potatoes that we measured. Remember that each of those bars represents an equal range of lengths. So we don't have 3.2 to 3.5 inches as the first bar all the way on the left, and then 3.5 up to 10 inches for the second bar, because that's not as meaningful when you look at it. So you can see here, just looking at this chart, it looks like the people who bagged the potatoes really put mostly 3.5 to 3.8 inch potatoes in there. So it shows us where most of the potatoes are. It's a little bit different than the box and whisker plot that shows us the range that our potatoes have. Instead, here we've chosen the ranges, and we want a chart that shows how many samples fall in each one of those ranges. Now don't worry that the histogram isn't a very pretty looking statistics bell curve. That green stripe is a very typical statistical distribution of how many samples occur at different ranges. And usually, you know, when you look at normal statistics curves, it kind of looks like a bell, or maybe a hat. You know, it looks kind of like that curve. They call it a bell curve, but it's officially called a Gaussian distribution after somebody named Gauss. So it's a Gaussian distribution, and that kind of a bell curve might not see if you have a small sample set. We really didn't take that many potatoes in our sample, but also we don't have to worry about that because of the central limit theorem. So that's a foundation of statistics, and I can talk to you about it real briefly. So the proof of the central limit theorem, which I'm not going to go into how to prove it mathematically, but just let me tell you what it ends up being. It shows that if we keep measuring many bags of potatoes, if we take many samples, sets, each with, let's say, 25, maybe 50 potatoes each, you just go ahead and take many bags. And every time we take a new bag of potatoes, we calculate the mean length, or the average length of all the potatoes in that bag. The central limit theorem says that the histogram of those averages, the more samples we take, the more it'll trend towards that traditional bell curve or that Gaussian distribution. So here, the curve, if you will, if I connect the peaks of my bar graph or my histogram graph, you can see it kind of makes that orange line, which has, well, honestly, it's got more than one peak, and neither one of them is really in the center. Whereas that bell curve, that seems to only have one peak, and it's right there in the center. And it's very symmetrical on either side. So that's a kind of a weird result that is true for just things in nature. Even if I take many bags of potatoes, some will have the orange distribution, that line I showed you right here, this histogram you're looking at. Some will have a different lumps in different spaces, different peaks, different number of potatoes of different sizes. But if I go ahead and take many samples, over time, that mean value, the average of the lengths of potatoes, will always trend towards this bell curve, this Gaussian distribution, which is kind of a weird result. You kind of think, really, can that happen? But the proof is left, mathematical proof is left for another time. But that's a very interesting result about statistics, is that things trend towards a bell curve, even though your particular sample might have that orange curve with doesn't really look much like a bell curve at all. So in our case, we're going to draw the histogram of just a single small sample. So we end up with more than one peak, and the biggest peak is not in the center. Perfectly fine, don't worry about it. Just know that the central limit theorem of statistics shows that if I were to take many more samples, I would go ahead and see that the a histogram of the average lengths of those sample sets would trend towards a bell curve distribution. So what can I tell by looking at this histogram? Whether or not it's bell-shaped or not, I can still tell quite a few things. So I can see that, look, there's a lot more potatoes that are within the range of 3.5 to 3.8 inches than there are potatoes, for example, in the 4.4 to 4.7 inch range. Even though the range in inches is the same amount, it's 0.3 inches in all the cases. But it just shows you how many of each range of lengths occurred in your sample set. So that's one very important thing. But we can also tell some other things by looking at a histogram chart. And one of them is what we call the confidence intervals. So let's talk about the confidence intervals. So I can go ahead and circle a whole bunch of ranges. Here, this blue box here circles all of the ranges, 3.2 to 3.5, 3.5 to 3.8, 3.8 to 4.1, 4.1 to 4.4, 4.4 to 4.7. Essentially, the whole range, the blue box, covers everything from 3.2 all the way up to 4.7 inches in length. It doesn't cover the 4.7 to 5 inches in length, but it covers everything in the, some range of ranges, if you will. And I'll literally just count the potatoes that fall in the blue box. So really what we're saying is that, let's say our total sample has 24 potatoes, our sample set, 24 potatoes, but 21 of them fall in this blue box. 21 of the 24 potatoes are less than 4.7 inches long. And 3 of the potatoes are more than 4.7 inches long. So 21 of them are less than 4.7 inches long. And how can I convert that into a percentage? So a percentage, percent, that's from the Latin, percento, meaning just multiply it by 100. So whenever I put the little percent symbol next to a number, it means I've multiplied it by 100. But what exactly did we multiply by 100? And it's really how many potatoes are in the blue box divided by the total number of potatoes. So there's 21 potatoes in the blue box, or 21 potatoes that are less than 4.7 inches long. And there's 24 potatoes total. So all I really have to do is basically take 21 potatoes, which is all the ones that are less than 4.7 inches, divided by the 24 potatoes, which is the total of all the samples in my sample set. And I come up with this number of 0.875. And people like to see that expressed as a percent, so basically I multiplied this by 100, or moved the decimal place, 2 spaces over. And that's how I get this 87.5% level. So if I were to go ahead and tell somebody, look, close your eyes, randomly pick a potato out of the bag, I would be 87.5% confident that that potato would be less than 4.7 inches long. I would be, basically, that's the confidence interval. This interval here is 87.5% of my data. So I'm 87.5% confident, or that's that confidence interval, that a randomly selected potato from my sample set would be less than 4.7 inches. So similarly, I guess the chances of it being more than 4.7 inches would be something like whatever 100% minus 87.5, or what is that, 12.5% confidence interval. That I only have a small degree of confidence that you would actually get a potato 4.7 inches or bigger if you randomly pick one. So very small chance of picking one 4.7 inches or bigger, and a much stronger chance or confidence that you would pick a potato that is less than 4.7 inches long. So the histogram allows us to do confidence intervals. Now, if it had been a bell curve, if you will, if it had been that hat-shaped bell curve, then I could do this sort of calculation even without drawing the histogram and even without counting the potatoes, because the bell curve is very regular in shape. The center is right in the peak is right in the middle or the center. It's symmetrical on either side, so it has an exponential function that can be actually calculated to draw the bell curve. So if my sample was a bell curve, I could actually figure out these confidence intervals automatically without even having to count potatoes. But it just wanted to show you how it's done by actually counting them. So much of statistics has to do with just counting how many things are in one bucket versus another bucket. This histogram itself, this whole drawing itself, is literally counting how many potatoes fall into each one of these bins. They call them bins, like a bucket, equally sized bins. 3.2 inches to 3.5 inches is kind of a 0.3 inch bin or range of values. And we just simply counted how many potatoes fell into each one of those ranges, and it allowed us to do things that are very sophisticated, such as create confidence intervals of what is the percent likelihood that we'll get a potato of that range of lengths, given the fact that we randomly select them from our sample set. So just be aware that a lot of statistics has to do with simply counting how many items are there. But it uses a lot of terminology and maybe pictures you haven't seen before. Don't be confused by that. Statistics is mostly all about counting things and going ahead and taking a look at their ranges. So just like the box and whisker plot, they are divided the number of potatoes into 4 parts, 6 potatoes each, and then showed you their length ranges. Here, the histogram, we divided the length ranges into equal parts. In this case, 1, 2, 3, 4, 5, 6 different equal parts, and then counted how many potatoes fell into each one of those bins or each one of those length ranges. So just be aware, much of statistics is just simple counting. And the idea of using these sophisticated calculus formulas to go ahead and create confidence intervals and to look up charts and to find the z-score, these are all fancy ways of using the fact that the curve is bell-shaped, and so therefore you can avoid counting the number of potatoes. You know, if it was bell-shaped, I could tell you what the 87.5% confidence interval range would be without having to count potatoes, because I would say, oh, it's a bell curve, I'll use this this logarithmic analysis or exponential table and look it up, but that's only to avoid counting it because it's precisely bell-shaped in its curve, and most items do tend towards that bell shape, as we learned with the central limit theorem. If we took enough bags of potatoes, eventually their average length of each sample set that we took would tend towards a bell curve. So it is a very, very useful thing, but don't be stressed out about statistics because of that bell curve. The bell curve is the natural tendency of shapes of things, but your histogram might be different. The fundamental thing about statistics is really just counting items, and then figuring out, well, what's the chances of me getting an item when there's 21 out of 24 potatoes are in my bag are within that range. Then I've counted, it's 21 potatoes out of 24, so really that represents an 87.5, sorry about my handwriting here, 87.5% likelihood of randomly picking a potato that is less than 4.7 inches long. It's just because I counted. So most of statistics is about counting, so don't stress out about it. I know students are sometimes stressed out about mathematics and statistics, but I'm hoping this explanation makes things simpler for you and realize that mostly statistics is all about counting things. So we can use Microsoft Excel to do everything that we've taken a look at so far. We can use it to calculate the mean, the median, the mode, to draw a box and whisker plot, to draw a histogram. Let's just go ahead and show you how that's done. So first you have to type in all of your measurements. So you can use pre-typed in values from your teacher, or maybe you're gathering statistics from a database. However it is, you have to have all the data in the Microsoft Excel, all the numbers. Notice that the last row that contains data is numbered row 25. But we know that we have only 24 potatoes. And that's because we use that first row to kind of put a label for what the data represented. So just make sure that you know whether or not, we call this a heading row. It kind of has a heading of what the name of the data is. So if you do have a heading row or several heading rows, you have to remove that from your total count of how many potatoes are in your sample. So Microsoft Excel calls the mean, that word that statistics word that we learned earlier, they call it the average. And honestly, most people in real life do use the same terminology, unless you're specifically talking about data and statistics. The word mean is mostly used for mathematical analysis. Most people in everyday conversations, they'll use the word average. So to calculate the average of a row of numbers, you'd select the cell where you want to put the answer, and then you type in equal sign, and then the word average, and then parentheses, A2 colon A25, and parentheses, and then you hit enter. So you have to start by typing the equal sign. That has to be the first character you type in the box, and that lets Excel know that it's going to be a calculation. And then in the parentheses of that average function, you're going to enter the range of cells by typing the location of the first cell, the A2, which is all the way up top here. So it's A2. That's the first data that we're going to use. And it goes followed by a colon. A colon is 2 dots. Don't confuse that with a semicolon, which is a dot and a comma afterwards. So you follow it with a colon to say that it's a range, and then you put the end of the range there. And the end of our range in particular is going all the way to A25. So all the way from A2 to A25, and what it'll do, it'll add up all those numbers and then divide it by how many numbers there are, in this case 24 of them. So that's how you calculate the average, and it'll go ahead and put the answer in the box where you type this information. To find the median, the function in Microsoft Excel is actually called median, so that's easy. And so you can see here our average now is a number because it calculated that formula. And we want to do the same for the median, and it's very similar. You work just the same way as the average function. You have to put the equal sign first, then you have to start typing the function name. Usually it'll fill it in, and you can click on it, and so you start typing MEDI, and by the time that you've done that, it's probably already figured out you meant to say median, so you can just double click here. And it gives you the parentheses, and the parentheses, same thing. You put the range in. I think there's also a way on most Microsoft Excel versions to go ahead and drag and drop, kind of drag your mouse with the button push to specify the range. But either way, it'll calculate the median. It went ahead and picked that value. To enter a box and whisker chart, what you do is you'd select all of the data. Basically, click your mouse on the first box and drag it all the way to the bottom box and let go. So you've selected all of your data. Then you would select the Insert button. It's a tab on this top. And once again, depending on your version of Microsoft Excel, these plots may be in different locations, or they might not even be available, so you might have to do them by hand. But I'm just showing you this version of Microsoft Excel does have it. So once you click Insert, then you would click on the Recommended Charts. We don't really want the recommended charts. We like to click on the All Charts tab, and then that shows all the different charts, and Box and Whisker, at least in this version of Microsoft Excel, is available. It shows you a little version of it there, and you just say OK, and that's how you insert your Box and Whisker plot. The histogram chart is created pretty much in the same way as the Box and Whisker. You would say Insert and Recommended Charts, so then you'd select All Charts, and then go down and click on Histogram. So you can customize your histogram using the Design and Format tabs at the top of your Microsoft Excel. And you can change the title and the colors and things like that. But I wanted you to take a look at some of the details of this histogram chart so that you can understand, customization. So let's take a look at these numbers down at the bottom of the histogram chart, and let's zoom in on that central bar here, and notice that the left parentheses is a curved parentheses, and the right parentheses is a square parentheses, otherwise known as a bracket. So what does that mean? That means that this column here represents the range of inches from 3.835 inches all the way to 4.385 inches. But it would not include a potato that had exactly 3.835 inches. So the curved means up to 3.835, but not including 3.835. So if you did have a potato that was exactly 3.835 inches long, it would have ended up in this bucket, or where you have 11 potatoes, not in this bin where you have just 8 potatoes. And the last bin here looks like it's got 5 potatoes. So 8 plus 5 is 13, plus 11 is 24. So here's basically all 24 potatoes. But you notice they've only chopped them into the 3 bins. Now you understand what the curve means up to but not including, and the square, which means up to and including. So in other words, if we had a potato that was exactly 4.385 inches, it would appear in this count, this center count here. So that's really what the rounded and square brackets mean. But you might not like having only 3 different bins or just 3 different ranges. You can go ahead and change that by using the format the axis. So you would go ahead and look to format the axis. This is the vertical axis that says how many potatoes, and this is the horizontal axis that says the size of each of those bins. So we're going to select the horizontal axis, the horizontal category axis, and we can customize that. If we don't like those automatically selected bin values, we just chop all of our data into 3 bins, I can go ahead and change that bin width, so make it 0.3 inches like we showed earlier with the hand-drawn one. Or I can change the number of bins. I can say, oh, I want it chopped up into 10 bins or whatever it is I want. So there's a number of different options here to go ahead and decide what you want your histogram to look like, both color and style, but also the bin sizes. And we use the name bin because it is basically counting how many potatoes would have this kind of range of length, and how many potatoes would have this middle range of length, and how many potatoes would have this top range of length. But what if I chopped it into many more ranges or fewer ranges? That's the customization that I mean. So now you know how to do mean, mode, and also the median. And you also know how to draw a box and whisker plot and a histogram chart. All of that in Microsoft Excel. You also know how to interpret the meaning of those values, and you also know how to use the diagrams to get even more information, including ranges for the box and whisker plot, and also confidence intervals using the histogram chart. So those are fantastic things, but they've only been looking at one of our measurements, the length, or univariate analysis, just how one item, uni meaning one, varies, variate, univariate. But we like to also have a bivariate analysis because our hypothesis, our theory, says that we think that potatoes get wider as they get longer. So in our next presentation, we're going to understand how to do analysis of multiple values, the length and the width. So we'll learn about a scatter plot diagram, and we'll also understand correlation. And these two things have to do with not just one value that varies, not just a univariate analysis, but a bivariate analysis of our statistics, how these two values might tie in with one another. So thank you so much for listening to this video. I appreciate you taking the time, and I hope we've made statistics just a little bit simpler for you.